Welcome everyone to the daily space for Friday, September 28th of 2018. I am your host, Dr. Andres Plazas, and today we're going to talk about some of the stories from astronomy and space. So we're going to start talking about galaxy clusters. And in this first story of the day, astronomers have used data from Chandra, from NASA's X-ray Chandra Observatory, and they actually have figured out a possible way in which galaxy clusters can get bigger. So galaxy clusters are the largest structures in the universe, and they're held together just by gravity. And well, galaxy clusters, they contain hundreds of galaxies, even some of them thousands of galaxies, of individual galaxies. But most of the mass in a galaxy cluster comes from hot gas, what you call intergalactic gas, intercluster gas, and of course from dark matter that we cannot see. But from the gas, you can get an X-ray signal. So in the particular study that we're talking about today, and in the image that you have on your screen, if you look on your left panel, we're actually looking at a galaxy cluster called Abell 2142, as seen by Chandra. And this particular galaxy cluster is embedded in a multi-million degree gas detected by this telescope, which is in purple. And then the center of the galaxy, you can see it in that elliptical blob. You look at more or less at the left part of your screen and then look at that elliptical blob. That's the center of the galaxy. But then if you look at the upper left part of the screen, you're going to see a group of galaxies that is actually being attracted by the powerful gravity of the cluster as a whole. So you can see a closer view of this smaller cluster of group of galaxies that it's being attracted by this larger cluster of galaxies. You can see a close-up on the right part of your screen. And one of the things that you can notice is the direction of the tail. It has like a little tail, little from our point of view, but the actual size of the tail is about 800,000 light years. And then that tells the researchers that actually that's what's going on. There's the powerful gravity of the galaxy cluster is attracting this particular group of galaxies that is in the upper left part of the screen. So researchers, they have identified a certain number of bright galaxies in this little group of galaxies. And they actually think that this is hot gas that is being stripped off from the group of galaxies, that is being it maintains its shapes thanks to a powerful magnetic field that are wrapping around it and are acting like a shield, sort of, in order to contain the gas. But then, as time, as as it gets farther away from the group of galaxies, of course, the magnetic field is not as powerful, and then the tail flares a little bit and starts becoming irregular. So yeah, in addition to this, the data by Chandra also confirms that two of the four bright galaxies that you can see in the some of the bright galaxies actually that you can see in this group, two of them actually contain rapidly growing and supermassive black holes. And yeah, at the same time, they have found a counterpart image with a visual images from the Sloan Digital Sky Survey. So the data by Chandra is in purple, and then all the other components that you can see in the blue, green, and red bands are from the Sloan Digital Sky Survey, and that's what they overlap here. So that's it for the first story of the day, and for the second story of the day, we're going to talk about strongly magnetic neutron stars. And this is an interesting story because a team of astronomers from Amsterdam, actually, this was a student, actually they have used data from the Very Large Array, the VLA, and the story is interesting because the same team of researchers last year they had published two articles that were suggesting that you could actually observe a strongly magnetized neutron star that was producing jets. And this is more or less what you're looking at the screen right now in this artist conception, in this simulation. And the interesting thing is that from the theoretical point of view, from the understanding, the theories that we had of these systems, this should not be possible actually, in principle. So then they published a paper a couple of years ago, last year, I'm sorry, they published two papers last year saying that it might actually be possible. And then in the research that we're talking about today, they have found experimental evidence that actually this might be the case. And then this is a paper that will be published, actually has been published already online and in Nature. And well, just backing up a little bit, so these jets, they're very high energy plasma streams that are blown into space at a very high speed from the immediate vicinity of maybe accreting, in this case, a neutron star or sometimes black holes. So in the context of this story, this accreting word actually means, as you know, that the neutron star is actually attracting the gas from another star that is orbiting next to it. So it's more regular stars. So these jets, they have been known for decades, but they have never been seen when a neutron star has a strong magnetic field, just until now. And there was a prevailing belief the prevailing belief was that the very strong magnetic field would stop the formation of the plasma outflows because the gas could not get close enough to the neutron star where the jet would be created. So in the past, people were thinking maybe you could have these jets if the magnetic field is not strong enough, because in that case, the gas in the accreting disk would have the chance to go into the star and then create these jets. But they have actually found evidence in this article that they're presenting in this article that actually even when you have these strong magnetic fields, you could have this type of jets. So, well, this doesn't mean, well, what does this mean? This means that we actually have to check or revisit the understanding of the theory that we had of the formation of these systems. So it doesn't mean that you actually have to discard right away all the theories, of course, so they completely start from scratch. But this is a result that is telling us that it will have to revisit the theories, and it actually fits well with a recently developed model in which the formation of jets is explained in a completely different way, and the magnetic fields is no problem. So this is a good confirmation, experimental confirmation of a new model that actually revisits the old theory that was prevailing with respect to the formation of these jets. So yeah, that was pretty cool. That was the second story of the day. And just to finalize, we're going to talk about the HyperSuperN camera survey. So this is a survey collaboration that actually has utilized weak gravitational lensing to give us its first cosmological results. So many of you have heard me talking about the dark energy and weak gravitational lensing in the past. And just to again give a short summarize, the observed accelerated expansion of the universe was discovered in 1998, and then by 2006, 2011, then people actually found more and more evidence that this is actually what was happening, that the expansion of the universe was going on in an accelerated way. And then we don't know what it is. We're trying to figure out what that is. And one of the ways we want to find that out is by using something called gravitational lensing, which is the distortion of light by any distribution of matter or energy in the universe. And in this particular type of cosmological studies, we want to use gravitational lensing to see dark matter. And you want to see it because, of course, by definition, you cannot see dark matter by electromagnetic radiation, but you can see the distortion that all the large-scale distribution of the universe, which is mostly dark matter, you can see the distortion that large-scale distribution is causing on background galaxies. And then by measuring those distortions, then you can figure out where the dark matter is. And then if you measure those distortions in different epochs of the history of the universe, you can figure out how the distribution of dark matter is evolving with time. And this is telling us about the dynamics of the universe. So we think that the accelerated expansion of the universe is due to something called dark energy that is causing this accelerated expansion. And the way that dark energy and dark matter work is in a way of sort of uh, disturbing or creating more structure in the universe. Dark matter is trying to get clumped, is trying to create more structure in the universe, whereas dark energy is trying to dilute that structure in the universe. So one of the things that we can do is use gravitational lensing to measure hundreds of millions of galaxies. Um, and then create these distortions and see how the dark matter actually evolves with cosmic time. So in this particular example, we're talking about the HyperSuperN camera survey. So this is a Japanese-led survey, although it also has researchers from the University of Taiwan and actually from Princeton University, from the American contribution. They have a very cool telescope in Mauna Kea. It's called the Subaru telescope. It's an 8-meter telescope. It has, the camera actually has about 800 million pixels. And this is the first data release. This is just 10% of the data of the survey. The survey is expected to finish about in the 2020 or something like that. And the researchers actually have found a result that is consistent with with the standard cosmological model, what we call the lambda cold dark matter model, in which the dark energy is explained by something that we call the cosmological constant. So one of the plots of the paper that you're actually looking at in your screen has actually the age of the universe as a function of, it has plotted actually in one of the axes the age of the universe, but one of the other parameters that we want to measure is the amount of clumpiness in the universe. And then as I said, the basic idea is that you can maybe measure a little bit of clumpiness or maybe a little bit more of clumpiness. There is a parameter, there is a number that you can measure that can tell you about that. And if you have less clumpiness, then that means that maybe you have more dark energy and vice versa. So the interesting thing about these results is that they have found a measurement that is consistent with another survey called the Dark Energy Survey. I have mentioned in the past that I am part of this collaboration, and in this collaboration we actually are using a telescope in the southern hemisphere to actually also try to figure out what dark energy is. We're actually using a telescope, a 500 megapixel camera in the northern part of Chile. And that's what you see over there as what you call as DES. And then there has been another survey called the Kilo Degree Survey that also has very similar goals. And then at the same time, you have the results from the Planck collaboration, which is actually doing measurements at a completely very different time in the universe. Planck actually gives us a lot of information about cosmology, but this information comes from a time when the universe was about 400,000 years old, as opposed to today, we're about at 13.7 billion years. So two things that to get away from this plot. First, the HyperSuperN camera survey is giving us measurements that are consistent to other completely independent surveys, the dark energy surveys and the kilo degree surveys, that gives us confidence in our cosmological model, and we're actually measuring something that makes sense. And then you see the second thing is that you see some numbers that are a little bit below what Planck gives you. So the mean points, so you can see that the points are more or less a little bit below what Planck gives you, but still they're not that far away from each other from the statistical point of view. So we could say that from the statistical point of view, all the data points are consistent. And then again, one of the most important points here is that Planck is measuring something at the very beginning of the universe, and what you measure with lensing of the large scale structure of the universe is something in the current times, relatively current times. So it's remarkable that these two very different ways of measuring the universe actually are giving you something consistent. So this is just basically the same plot that we were showing yesterday. It's just don't get maybe too stressed out about the axis and stuff like that, but it's just telling us that the results are consistent. So red is the HyperSuperN camera survey, and green is DES, and you can see that these areas, what are you plotting here? We're plotting actually the amount of matter in the universe versus how clumpy the dark matter is. And in a perfect world, when you didn't, if you didn't have any experimental error or anything like that, everything would overlap on top of each other. And if your theory makes sense. Most of the work that you do in these surveys, like DES and HSC, is actually to try to understand the experimental statistical errors that you can make when you're doing this type of measurement. This is like maybe some of you may have taken this, I don't know, experimental physics class in college or in high school when your teacher tells you that you have to measure all the error in the ruler or in the weights or in the scale. Well, this is actually very important. This is actually what we're doing in these cosmological projects. And then most of the papers that are going to be published is to try to convince ourselves and to convince our peers that we understand the errors, so in such a way that we can actually trust what we're actually measuring. And then, as I was saying, this plot is just basically showing more or less what I was just telling you, that the two results are consistent. They're not that consistent with Planck. They don't overlap that much, but it's still within statistical errors. They're consistent. There is nothing to report yet. It would be very interesting, and this is what's going to happen in the next few years. In the next few years, we're going to be able to we're going to have more data. As I mentioned, HSC only has reported like 10% of the data. DES is actually going to report all of its data in about 1 or 2 years. And we're going to be able to shrink the size of these ellipses, of these banana-like ellipses. That means we're going to be able to shrink the size of the error bars. And then if we still see that Planck and the blob from Planck and the blob from the other surveys, they don't overlap, then we start like thinking like something's going on, because they should overlap if our current cosmological model makes sense. Just finally, just to see how tiny the difference is, as I was telling you, so we have this standard cosmological model, and there are a lot of different parameters. And one of the parameters that is constrained by the weak lensing is, as I said, the clumpiness of the dark matter. How clumpy it is versus how smooth or uniform it is. And as I said, there was a slight difference between what HSC found and what Planck found. And then you can simulate that. You can take your supercomputer, then you can give all your cosmological parameters, and then you can get a simulation of the large-scale structure of the universe, which is what you're seeing right now on your screen. On the left-hand side, you see what you're finding with the HSC. On the right-hand side, you see what you find with Planck. And then maybe at the resolution of your screen, you're going to tell me it looks exactly the same. If you squint a little bit, you're going to see certain differences in the clumpiness and in like these actually filaments and the bright spots here are actually the dark matter, right? And then you're going to see a slight difference, but overall, they're both consistent. So that was just to illustrate the type of things that we're actually trying to measure. This is just one of the parameters. There are many other parameters that are being measured. And one of the things that I'm looking forward is to more data from DES. We're actually getting ready to release a couple of papers in the next couple of months and weeks that not only uses the result from weak gravitational lenses, but we're also using other types of tools or techniques to learn more about dark energy. There are different ways to learn more about dark energy, and one example is the supernova explosions. And you get more constraining power when you combine all these different independent probes. And we call them independent from the point of view that the systematic errors from each one should be different, in addition to the fact that they're different probes by themselves, by definition. So, okay, that was the daily space for today. So I hope you guys enjoyed it, and let's see if you have some questions or some comments. I'm gonna look back at the chat. So I already said hi to Fenrik and to Hani, and hello, Bad Panda Bear. Hello, Guido. Hello, Ironheart. Is this going to lead to a lot of star formation? Yes, that's one of the triggers. Maybe you're talking, I think you're talking about the first story of the day where you had this group of galaxies being merging with the other galaxy cluster. And yeah, this is one of the triggers of a star formation. So I would expect that the star formation rate increases in this type of, with this type of events. Twitch is extremely twitchy on your end, Guido. Sorry for that. I don't know. I think I'm streaming at 328 or something like that, like a small rate. So sorry for that. Hello, Susie. Hello, Adam. Adam altogether. What is the furthest distance from us that gravitational lensing is useful, like the furthest object that could be used for this purpose? So there are two things. So here we're talking about weak gravitational lensing of the large-scale structure of the universe. And here, this is useful for at an age where the universe was about 5 or 6 billion years old. Because we also want to look at we want to probe at the time when dark energy started dominating the mass energy budget of the universe. So at the beginning of the universe, dark energy, as we think it is as a cosmological constant, was subdominant. At the beginning of the universe, we had that radiation, that photons were dominating the dynamics and the evolution of the universe. And then as the universe expanded and cooled down, then dark matter started dominating. And then just until about 5 billion years or so, dark energy started dominating. And then these are the epochs that we can probe with weak lensing. And then, however, then if we stop talking about weak lensing, we can use a strong lensing from an individual cluster of galaxies, and we can use that cluster as a cosmic telescope actually to see the magnified, distorted image of a galaxy that is very, very far away, like very close to when the galaxies started to very form in the universe, just a couple of hundreds of millions of years after the Big Bang. So you can do that with a strong lensing, with just one, with a strong gravitational lensing, with just one galaxy cluster as a cosmic telescope. But what is happening here in this study that we're talking about is we actually use weak gravitational lensing, in which you actually need hundreds of millions of galaxies in order to detect the signal, because with just one signal, with just one galaxy, the signal is so weak that you cannot tell if it's distorted due to gravitational lensing or the galaxy itself is just elliptical by that. So it's the same phenomenon. It's called gravitational lensing, but then there are different types of gravitational lensing depending on how strong the signal it is. So you have, of course, strong lensing. These are just arbitrary labels, but they're useful. Strong lensing, weak gravitational lensing, and then sometimes you hear in the news people talking about micro lensing to look for exoplanets. So Ferrin points out that the large-scale structure of the universe looks like neurons, and yeah, actually that makes sense. And I believe, and actually this is very interesting, I believe that some of my colleagues in cosmology and they have found similarities in theories, in cosmological theories, with theories in neuroscience. And I don't know a lot about that, but I've been wanting to investigate more about this particular topic. So Hani is asking, so is this saying that the universe was just as clumpy in the past? This is actually measuring the clumpiness of the universe right now. And the universe actually was less clumpy in the past. So when I was saying about Planck, I should have mentioned, so you measured Planck from an epoch very early in the universe, as I just mentioned. This is all the information that you get from the cosmic microwave background. But then maybe I forgot to mention that what you actually do is that you, using that data from the early universe, you feed a cosmological model, and then you extrapolate with those cosmological parameters. You extrapolate to what the universe should look like today, and then you compare with other proofs of the universe that actually measure in the current universe, which is what these weak lensing surveys are doing. So when you see at this, what it says Planck preferred universe, is like using the parameters that we inferred from data from the early universe, and then letting run our cosmological model in our simulation. This is what we should observe today. And then you compare with what you actually observe today, or with, more exactly in this case, with the parameters that you derive from this other survey, and then you produce two different simulations, and you compare them one with each other, which is what you're doing right now. Is it fair to assume that the distribution of normal matter takes on the same distribution of dark matter presented in the dark matter simulations you're showing? Yes, to a first level it is. So actually, what we don't see dark matter, and then one way of seeing dark matter, as I just said, seeing, of course, in quotes, is through gravitational lensing. But the traditional way people do is actually measuring the galaxies that we can see. So actually, people measure the large scale distribution of galaxies, of the luminous matter, and then we assume that there is like they're coupled, that this distribution is coupled to the dark matter. It is actually the dark matter that is creating all these potential wells that are actually modeling where the luminous matter is going to fall. So usually people, to first approximation, say if you measure the distribution of galaxies, of luminous galaxies, you should have a linear bias. It's actually called the bias. You should have a linear factor. If you multiply the distribution of galaxies, of luminous galaxies, by a linear number, you should get the distribution of dark matter. But that's just the first order. And then there are more complicated expressions. No, this factor, or this relationship between the luminous matter and the dark matter, actually can become what we call nonlinear, and it can have a slightly more complicated relationship. But the first order, you can say that the distribution of dark matter is traced by the distribution of luminous matter. Han is asking, I did not realize there was a difference between how strong and weak lensing was done. Yes, from the mathematical point of view, well, it's all weak lensing, but in principle, gravitational lensing is actually a nonlinear effect. And by what I mean by that is, like, when you look at a strong lensing, you see multiple images, you see very clearly the distorted galaxies. But then as you get away, for example, from the center of a galaxy cluster, the distortion starts to be smaller and smaller, up to a point where the distortion, you cannot see it by eye. That doesn't mean the distortion is not there. There's still a coherent distortion in a certain part of the sky, and that is still telling you about the distribution of dark matter at that point, or between, of course, the galaxy that is being distorted and the observers, which is us. So the techniques and the systematic errors are slightly different. Eventually, will all the dark matter be in separate blobs instead of filaments? That depends. The future of the universe depends on the actual components of the universe. So if dark energy actually starts dominating, then yeah, everything is going to be separated from each other, and this is one of the possible scenarios. The scenarios like a cold freeze death, when dark energy takes over everything, all the galaxies that we see, they just, many of them, actually eventually all of them, they're gonna go farther from what we call the horizon, or what we actually see, and it's just gonna be as isolated, depending on whether dark energy ends up dominating or not. So there are different scenarios. If we find out that actually dark energy changes with time, and then maybe is not a cosmological constant, or it has been consistent with a cosmological constant up to now, but then in the future it's going to maybe decay in something and it's going to disappear, then the dark matter maybe could start dominating, and then you're gonna find a clumpier universe. And maybe if you have enough mass, then you have a critical mass that is gonna create a big crunch or something like that. So in the end, it's going to depend on the actual distribution of the different components that make up in the universe. Currently, that distribution, as we have said several times, is about 70% dark energy, 25% dark matter, and the rest regular matter. All right, everyone. Uh, okay, thank you so much for your comments and your questions. So this has been the Daily Space, and as you know, it's a production of CosmoQuest, part of a project of the Astronomical Society of the Pacific. So please give us a like if you want to support us, and please subscribe if you like what you see. And we're coming back with the Daily Space next week at 1 p.m. Eastern Time. So I hope you guys have a great end of the week, and I'll see you next time. Bye bye, everyone.